Okay, thank you for introduction, and I really would like to thank the organizers of forum for invitation to give presentation in this very important meeting. And I will speak about some innovation in airborne geophysical technology. No, I would like to start that airborne geophysical methods are extremely important because using airborne techniques, we can cover large area very economically with limited cost and obtain results which otherwise very difficult to get using the ground data. However, until recently, most airborne data was interpreted only in terms of actually maps of the observed data. For example, for magnetic data, magnetic maps were analyzed. For electromagnetic data, very simplistic laid Earth interpretation was done. This example of the map of EM data collected in the alien Democratic Republic of Congo, and target was conductive mineralized black shale. But if you look at this map, you cannot find the shale because these maps will tell you even horizontal location, you cannot see this. So important, and this will be focus of my presentation, that of course very important to collect good data using drones or helicopters or fixed-wing airplanes, but then what to do with this data? And this is actually the subject of my presentation. Because in fact, what you can do if you apply computer simulation, you can simulate the physical geological property of the subsurface and predict the observed data which would be produced over specific geological formation. And then you can compare this data with your observation. And by iteration, you can get very good fit. And then you will get real 3D model of the subsurface. And this is a horizontal slice of the 3D model at a depth of about 300 meters. And then you can see the shale. So you can compare. Try to go back. You can compare. This is what you see in the map, and this is what you can see after interpretation. So it's a huge difference. And so this is what is my talk about. And actually in this talk I will review some recent developments and identify those advances which have resulted actually in paradigm changes in airborne geophysical surveys. There are two aspects. First aspect is collecting multi-physics data. Because, you know, until recently, people collected magnetic data, but they are responsible for magnetic properties of the rocks. Or gravity data, they will give you information about density. Or electromagnetic data, they provide information about conductivity. At different sides of the same geological structure. And each of these techniques provides a very non-unique solution. We know very well, geophysicists, that you can find many models which could generate the same data. But by using multi-physics data, we reduce this uncertainty and we come up with more reliable, more robust solution. So this is the first advances. And second, of course, this what we call in geophysics inversion. The process which I described before, constructing the 3D model of subsurface based on computer simulation, in mathematics and geophysics called inversion. And what is important, 3D. Because there are quite a few techniques out there for very simplistic model of the Earth, like horizontally laid Earth. But what we develop full 3D realistic modeling of subject using all different type of the data. As a case study, I will show the results of the project which we conducted here in Saudi Arabia. We call it Glass Earth Saudi Arabia project, and explain you later why. But before, I just show a simple picture. This is a airborne geophysical system, and it could, we can use different platforms, fixed wing, helicopter, drones, and different sensors, magnetic, gravity, electromagnetic, etc. As example, airborne platform, for example, how it works. You have airplane, you have this shown by red transmitter loop, it generates the pulse of electromagnetic signal. It propagates through the Earth, then reflects back, you measure the response, you obtain the data. But the key is how to transform this data in the model, in the real geology. And this is what we were working. We will develop joint inversion of multi-physics data. And this joint inversion much more powerful than the results provided by individual data set alone. And so this is really very powerful technology for risk reduction and success of the discovery of mineral deposit. Now, as illustration, I will speak about this project which we conducted in collaboration between Technoimaging. Actually, Technoimaging is a US-based company. We located in Utah, in Salt Lake City, and CAX, King Abdulaziz City of Science and Technology, here in Riyadh. So we conducted this survey, which involved acquisition, processing, interpretation, airborne EM, gravity, magnetic data over about 8,000 square kilometers area over Arabian Shield. And the goal was to study the top kilometer of the Saudi Arabian landmass to provide roadmap for natural resource exploration in this area. So this is workflow of our project, but I think this workflow can be applied to any geophysical survey. You start with country scale. You evaluate, geology and prospects of different areas of the country. You select the area for regional study. Then you go to regional scale. You conduct a airborne survey over about areas, many thousand square kilometers. Then you go to deposit scale. You conduct more detailed survey on the area about maybe 10, 15 square kilometers. And then you drill. So, and this is where we have this green effect, because instead of drill, and having hundreds of drill holes, very expensive and very environmentally damaging, you select the optimal position of your drill, you save money, you save environment, and you have the best product available. So the first stage, we analyzed with our colleagues in CAX, general geology, and selected area shown by red. It's close to Medina. Actually, there are quite a few very well-known mines in Saudi Arabia. Solomon mine is nearby, by the way. Mahal Dahab. I'm sorry, my Arabic is not good. So anyway, so we selected this area. It's, as I said, 8,000 square kilometers roughly. So then, next step, regional scale. So we flew on survey. This is the lines of the survey. This airplane, this data acquisition was done by our partner, Spectrum, South African company. So they collected this data. And we process, quality control, analyze the data, design survey, and worked jointly with them. They acquired the data. These lines and flight lines over this area, so this regional scale. So we got the data. By the way, this is how it looks like from the airplane. It's all deserts, you see. There is no surface expression of subsurface geology or potential mineralization in this area. If you go over, walk over, or fly over, you don't know where is the target. It is 8,000 square kilometers. Now, what we did, we developed in Technoimaging what we call glass earth technology, which provides proprietary data acquisition imaging systems, which make it possible to make transparent the earth. And we call it, it's like metaphorical glass earth. Glass means transparent like glass. And so then we can see what is inside. In this example of this 3D view of subsurface formations produced by the data collected in the plane, example shown here. This is huge model. This model of about, as I say, horizontal size, 8,000 square kilometers, depth 1 kilometer, roughly. This is a magnified area, one of the section. And you can look inside. Really, you can see here, on the left, you can see conductive overburden. Red means more conductive. Then you can see clusters of mineral targets here. You can see alluvium cover. So, and you can actually rotate. You can do whatever you want with this model. You can slice it. You can look from underneath if you wish. You can walk in. There is some technique. You can put glasses and walk inside the model and just walk inside the geology. And this is an example of this model in 3D. How to push so that it's rotated. I try to push, but... Oh, OK. So you see, this is 3D model, and I'm very close. 2 minutes will be enough. So this is this large model, and again, we slice it in this direction. You can slice it any direction you want. It's 3D image, volume image of the subsurface. This is glass earth model of 8,000 kilometers of Arabian Shield. Then you can focus on specific area. We selected some area of interest, and then you can see the target. You can look more carefully, and then you can zoom in on specific area and select the target. Then you can pick up the target. And this will be our phase 4. And you can drill. And we did it.
And we pick up target from area of 8,000 square kilometers. We selected actually 3 drill holes, but we drilled just 2, diameter 10 centimeters, and we pick up mineralization. It's mineralization of the same type as Solomon mine, is a mine. It's quartz veins with pyrite, chalcopyrite, and gold there. So we were able to resolve this. So I'm finishing. So the Glacios project has followed exploration workflow from countrywide selection through drill, hole targeting, and discovery of blind mineralization based on airborne data. The discovery would not have happened without this airborne technology because there is no surface expression of the mineralization. And 300 meters drill hole was sited in the original area of nearly 8,000 square kilometers. And this mineralization of the same type as Mahler Hub, epithermal gold and silver deposit, located actually not far from our discovery. And there are several other potential deposits in the survey area defined by the Glacios pilot project. So I think this technology could be very beneficial for Saudi Arabia, not only here, but other places, but specifically here, because it's so challenging to get in this desert area, and cover 8,000 kilometers on foot. It would take, I don't say how long. This project took 1 month. Data acquisition, processing, and interpretation in other months. Thank you very much.